Hi guys, we're talking about heat transfer and thermal processes today. So I want to look at another of those famous pressure versus volume diagrams with a gas cycle. So let's take this triangular gas cycle that I'm seeing on AP Classroom. And it looks something like this. And let's put some numbers on it this time. Let's say this is 200,000 pascals. I'm going to put pascals label there. I'm going to put 10 to the negative 3 meters cubed as my unit down here. I could have done something like that up there. So let's call this as 1, and we'll say this one is 3. So that will be 1 times 10 to the negative 3 meters cubed, or 1 liter if you'd like. So let's just label our points so we can talk about these easier. So when we go from A to B, from here to here, how does our internal energy change? Well, we can say the change in internal energy is the heat plus the work done on the gas, right? So, but this is an isochoric process, which means my volume doesn't change. I know that the work done on the gas is P delta V. So since my volume didn't change, I know that no work is done in an isochoric process. We can say W equals 0. So what about my heat, though? Like, if my internal energy changes, I have to have a heat exchange, right? Because how do I know my internal energy changes? Well, I mean, there has to be some reason I have less pressure I'm exerting on the walls, right? My gas is because the pressure is exerted from molecules in your gas hitting the wall and bouncing off. This means that they're hitting less often, or maybe they're not hitting as hard, or maybe both. Probably both. So it seems that there must be some reason that the molecules in my gas are moving slower. So I must have had some heat exchange. Well, how do I figure that out? Well, one of the things I can do here is I can actually figure out what the temperature differences are at these points. So let's say I have to define how many moles are in my gas. So let's just say that I have 0.1 moles. Just keep this small. We'll say N equals 0.1 moles. And I can figure out what my temperature is at each of these points, because I know the pressure, I know the volume, and I know the number of moles. So I know P, V, N, and R is a constant. So at point A, P, V equal, let's say A for each of them, and we're going to assume N is a constant. So this will tell me the temperature at point A. So if I want to solve for this temperature, I can say then that, and plugging in numbers, I'm going to get pressure is 2 times 10 to the 5th. The volume is 1 times 10 to the negative 3rd. N is 0.1, or I could write that as 10 to the negative 1 if I wanted to, and R, as always, is 8.314. I'm going to put that into my calculator real quick, and I'll be back. I completely forgot to define the pressure at point B, so we can call this pressure 2, or pressure B. Pressure BC, whatever you call it. I'm going to say this is just half of the other value, so 100,000 pascals, or 10 to the 5th pascals. And now I'm going to go ahead and calculate the value of B, but we found it just putting the numbers in here. The temperature at point A is 240.6 kelvins, which we can round to 241. And we don't actually need our calculator to figure out the temperature at B, because all of these three are the same. And this number is just half, so I can divide the temperature by 2, and this is going to be 120.3 Kelvin. So pretty cold. Okay. So how do we get heat exchange out of this? Because this is temperature, and heat and temperature are different things. Heat is a measure of energy, and temperature is, tells you what what something feels like, right? I guess temperature is related to the heat. It depends on each other. We've done that form before. So I can say the heat change is going to be Q equals the mass times the specific heat capacity times the change in temperature. So I can figure out how much heat has flown in if I know the specific heat capacity. So let's pick a value for specific heat capacity. Let's say this is oxygen gas. That tells me that at constant volume, so the specific heat capacity of oxygen at constant volume is going to be 652. And yes, I did just go look that up. But there are some pro tips and tricks you can do to get a really, really good estimate based on knowing if it's a monatomic or diatomic molecule. But that's a discussion for another day. So that is going to be joules per kilogram Kelvin is the unit for specific heat capacity. So then I would just want to figure out the heat exchange. I would say, I'll just put these in. So now I need to figure out what my mass is, right? So I'm just going to step to the side here and figure out the mass. Because I know I have 0.1 moles. This is oxygen, which is a diatomic gas. So I know the atomic mass of oxygen is 16 grams per mole of oxygen. Ooh, that's a Q. Just make that nice round O. But I want to say I want to get O2, right? So I want, there are 2 oxygens per O2. This is, 1 second. Okay, I messed it up. So I don't want to put the grams of oxygen, I put moles of oxygen. So then here I want to say I've got 2 moles of oxygen per 1 mole of O2. Once you get your units right, it's important for these. And so that's going to tell me that I have 32 grams per mole of O2. But I want kilograms, right? So I want to just say, that means I'm going to change the kilograms. So I want to do 1 kilogram per 1,000 grams. And lastly, I actually have 0.1 moles. So I need to multiply this by 0.1 times, to get an absolute value. All right, so this is going to give me a number. So it's going to be 32 over 1,000 times 0.1, so 3.2 over 1,000. So that means I have a mass of 0.0032 kilograms. Because gases are light, that makes a lot of sense when you think about it. So if I take this and put this in here, 3.2 times 10 to the negative third kilograms times 652 joules per kilogram Kelvin times my change in temperature. It's going to be 120.3. That'll get me how much heat I have exchanged. And I should specifically note this is a negative temperature here, change in temperature here, because I've got colder. I've gone colder. So after putting this into my calculator, this tells me that I have lost 200 and I think it was 51 joules. I might have to check this again because I completely forgot after typing it in my calculator. So I've lost 251 joules of heat to the environment. So my gas was hotter and has been losing that heat and exchanging it with the surrounding environment. So I think I'm going to put a break in the video about there because we've reached 10 minutes, and I'll just pick up right where we left off on a new video. See you in a bit, guys.